All right, welcome to another deep dive. And this time we're taking a look at, well, it's a pretty hefty book all about math, content, the methods, the history. But we're going deep.
Definitely. This isn't just, brushing up on your times tables. This is for those who already kind of get the basics, but want to know, like, why does it all work the way it does?
Exactly. That's the whole point of these deep dives. Like, we're not just going to skim the surface. We're trying to unearth those hidden depths of, well, in this case, math. The
Yeah.
kind of insights that maybe make you rethink what you thought you knew.
Yeah, I think even if you're, pretty good at math, you might find yourself surprised by some of the stuff in this book.
So let's just jump right into it. And I think a good starting point is this question that the book brings up pretty early on. What is a number? I mean, we use them every day, but have you ever stopped to think, like, what is it really?
Right. It's one of those things you just take for granted. But the book makes this really interesting point that when you get down to it, when you're looking at numbers abstractly, they actually get their meaning from their relationships to other numbers.
Okay, so it's less about the number itself and more about its place in a network of relationships.
Yeah, exactly. It's like the book uses the example of the number six. It's not just six hanging out on its own. It's five plus one, it's three times two, it's a factor of 30. All of these relationships are what actually give the number its identity.
Okay, I see what you're saying. So it's almost like each number is a node in this
Yeah.
massive network, and the connections are what give it meaning. But how does that abstract way of looking at it apply to, I don't know, someone who's not necessarily a mathematician?
Well, this whole idea of relational thinking, it's actually incredibly powerful, and it goes way beyond just math. It's how complex systems are built from simple elements.
Interesting. Like how so?
Think about a computer network. Like each device in that network, its function comes from how it connects and interacts with all the other devices. Or even a musical scale. The relationships between the notes, those intervals, that's what creates harmony. It's all about those relationships.
Right. It's like this underlying principle that's kind of weaving its way through all these different areas.
Exactly. And it just highlights the elegance and the interconnectedness of mathematical principles. You see it popping up everywhere when you start looking for it.
Now, the book also has this fascinating table. It shows how different cultures throughout history have represented numbers. You got the Egyptians, Babylonians, Greeks, Mayans. I mean, it's like a visual history of math.
It really makes you realize that our system, our Arabic numerals and the decimal system, which feels so fundamental to us, it wasn't inevitable.
Right. It's just what we're used to.
Exactly. It spread because it had practical advantages for calculation and communication. So it just shows how even in math, history and human needs have a part to play.
It really makes you wonder what other things in math that we take for granted might have been different if history had played out another way.
It definitely challenges you to look beyond what you assume is fixed and absolute, even in a field as seemingly absolute as math.
Okay, so let's move on to ancient Greece. Now, the Greeks, as the book describes, were totally obsessed with geometry. They even went so far as to solve algebra problems geometrically. Can you imagine that? Using shapes to solve equations.
It's pretty remarkable. Euclid's Elements, for example, that whole work is a masterpiece of geometric reasoning. But as we move into the 17th century, there's a big shift. You've got Descartes coming along with his Cartesian coordinates, and that essentially, brings geometry under the domain of algebra.
So it was like a power shift, like algebra kind of took over.
In a sense, yeah. And this leads to the development of, now it sounds intimidating, but abstract algebra. And this is where things start to get really interesting because it's about expanding the scope of what math can describe.
Or break that down for me a little bit. What exactly is abstract algebra? Because it sounds very complex.
It's about moving beyond just working with numbers and traditional arithmetic. We start dealing with sets of objects and operations, and those objects, they don't have to be numbers. They could be shapes or something else entirely. And the operations, they don't have to be addition and multiplication. It's about looking at the structure and patterns of how those objects interact.
So it's like a whole new level of abstraction.
Exactly. And this leads to some incredible breakthroughs. Like, suddenly we can start studying spaces that are beyond our familiar three-dimensional world.
Okay, so abstract algebra is what really opens up all these new dimensions of mathematical exploration, quite literally new dimensions.
Yeah, it's a huge leap, and its impact is felt in fields like theoretical physics, computer science, where the objects of study often defy our everyday intuitions about space and quantity.
All right, well, next up, we've got functions. The book describes them as the abstract image of how one magnitude depends on another.
Right, like the classic example is a falling object. The distance it falls depends on the time it's been falling, or, think about energy or heat. These are things that change based on other factors.
Right, so it's all about those relationships between changing quantities.
Yeah, and what's fascinating here is the emphasis on abstraction. Mathematicians, they're not just interested in a specific formula like the one for a falling object. They're looking for that general form of dependence, that y equals fx. That simple equation captures the essence of countless real-world phenomena.
So it's like a universal language for describing how things change and interact with each other.
Precisely. And by thinking about functions in this abstract way, we can unlock a deeper understanding of scientific models and predictions. We start to see those underlying patterns governing change across all these different fields.
Okay, that makes sense. But then the book takes us on this whirlwind tour of new math, throwing out terms like Lobachevsky in space, set theory, topology. It's a lot to process.
It's definitely a head-spinning array of concepts, but the key takeaway is this. Modern math, it isn't just about solving specific problems. It's about exploring all possible quantitative relations, even the ones that seem unreal or divorced from our everyday experience.
So are mathematicians kind of pushing the boundaries of what we even consider knowable with this?
Absolutely. And this shift in perspective, you see it echoed in fields like theoretical physics, where the very definition of reality is constantly being challenged.
It's almost like math is a tool for not just understanding the world, but for expanding our concept of what's even possible.
It's a powerful tool for imagining and exploring new possibilities, both within math and beyond.
All right, now for a concept I'm sure even our genius-level listeners will appreciate, calculus. The book mentions this ancient problem of finding the area under a curve, which, sounds pretty
It
niche.
does, right. But it turns out to be a lot bigger than that.
Oh, I bet.
This seemingly specific problem, it gave rise to one of the most powerful tools in mathematics, calculus. And what's incredible is that it uses the concept of infinity to solve real-world problems, like describing motion and forces in physics, or designing bridges and airplanes in engineering.
So we're taking something as abstract as infinity and making it work for us in very practical ways.
It's a testament to the power of mathematical abstraction. And even if you're not a mathematician, understanding the principles of calculus, it's beneficial because it underlies so many of the technological advancements we rely on every day.
Okay, I gotta admit, this next one is where I started to get a little lost. The book introduces the argument principle and complex numbers, which, unlike our familiar numbers, they don't just sit on a line. They wind around the origin and the complex plane. I'm not even sure what that means.
It sounds like something out of a science fiction novel, right? But stick with me here because this is where it gets really fascinating. The argument principle, as the book describes it, it links the number of roots of a polynomial to the winding of the corresponding curve in the complex plane.
Hold on. So the number of times a curve wraps around a point is somehow connected to the solutions of an equation.
Exactly. And this seemingly abstract idea, it has real-world applications like instability analysis and control theory. It's used to design systems in electrical engineering and aerospace to make sure they operate in a stable and predictable way.
Wow. Okay, so we've got these abstract mathematical concepts that are actually having these very concrete implications in building the technology that shapes our lives. That connection that's blowing my mind a little bit.
It really highlights how math's beauty often lies in these unexpected connections between seemingly disparate concepts. And those connections, they can have profound practical consequences.
It's like math is this hidden code that unlocks the secrets of the universe. And the more we decode it, the more layers of meaning and application we reveal.
That's a great way to put it. And it's that sense of wonder, that pursuit of understanding that makes math so captivating, even for those who might find it challenging at times. Welcome back to our deep dive.
We're picking up where we left off with this fascinating book about mathematics.
Last time we were talking about how math it's really about so much more than just, calculations. It's about relationships, patterns, these abstract concepts.
And we even ventured into the realm of like complex numbers and the argument principle. Still trying to wrap my head around that one.
It definitely stretches the imagination a bit. But today, I thought we could delve into how math helps us understand the universe itself, from the tiniest particles all the way up to the vast expanse of space.
Sounds good to me. The book delves into how calculus uses the concept of infinity to solve real-world problems, which is just wild to think about.
It really is. And calculus actually emerged partly from this age-old problem of trying to find the area under a curve. And to solve that, well, mathematicians had to grapple with this idea of infinity, dividing a curve into infinitely small segments.
It's pretty incredible how something so abstract can lead to such, practical solutions. It's like a bridge between the theoretical and the concrete.
Calculus is a perfect example of that. It might seem counterintuitive at first, but it gives us these incredibly powerful tools for understanding the world around us.
Like a secret language that unlocks the mysteries of physics, engineering, you name it.
Absolutely. And speaking of physics, the book also touches on the theory of relativity, which, as we know, completely revolutionized our understanding of space and time. And math is absolutely essential to even begin to grasp those concepts.
Right. Einstein's theory really throws everything we thought we know about the universe out the window.
It does, and it relies heavily on the idea of non-Euclidean geometry, which, challenges the assumptions of the traditional geometry, the kind we learned in school with parallel lines and right angles.
Oh, yeah. I remember Euclidean geometry. It all seems so neat and tidy. But non-Euclidean geometry, that throws all those neat rules out the window, right?
Not entirely. Euclidean geometry still works within certain limits, but Einstein showed that in the presence of these strong gravitational fields, space and time actually become warped. So we need non-Euclidean geometry to describe that curvature.
So it's like Euclidean geometry is a flat map and non-Euclidean geometry is a globe. It's a more accurate representation of, the curved surface of the Earth.
That's a great analogy. Non-Euclidean geometry helps us visualize and understand this curvature of space-time, this curvature caused by massive objects like stars and black holes.
It's amazing how math allows us to conceptualize things that are so far beyond like our everyday experience.
Exactly. And it's not just about describing what we already observe. Math also has this incredible power to predict phenomena that we haven't even seen yet.
Like how mathematicians predicted black holes long before we had the technology to actually observe them.
Precisely. And it goes back to that idea we touched on earlier, how modern math is about exploring all possible quantitative relationships, even the ones that seem at first unreal.
So mathematicians are like explorers, charting unknown territories in this world of abstract concepts. They're pioneers pushing the boundaries of what we think is even possible.
I like that, pioneers. And those explorations, they often lead to these groundbreaking discoveries that reshape our understanding of the universe. It's a testament to the power of pure thought.
It really highlights how interconnected knowledge is. You have this abstract pursuit of mathematical truth that can have this profound impact on our concrete understanding of the physical world. It's pretty mind-blowing when you think about it.
It is. The book also takes us on a journey through the history of mathematics, showing how different cultures and civilizations have contributed to its development.
It makes you realize how math is a collaborative endeavor, really, built up over centuries by all these brilliant minds.
Right. We see how mathematical concepts have evolved from, the ancient Egyptians and Babylonians to the Greeks, Indians, Arabs, and Europeans. It's like a tapestry woven from the contributions of countless individuals across history.
And it underscores how math is truly a universal language. It transcends all those cultural and historical boundaries.
Speaking of universal languages, let's circle back to the concept of abstract algebra. We touched on it briefly before, but I think it's worth digging a little deeper.
Yeah, I'm still a bit fuzzy on what it means beyond the basic definition.
Think of it this way. Abstract algebra is a way of generalizing those familiar concepts of, operations like addition and multiplication.
So instead of just working with numbers, we can apply these operations to, other mathematical objects. It's like expanding the toolkit.
Exactly. Abstract algebra deals with these sets of objects and the rules that govern how they interact. Instead of just looking at specific numbers, we're looking at the structures, the patterns of interaction themselves.
Okay, so the book mentions groups, rings, and fields. What are those exactly in this context?
Those are different types of algebraic structures. A group, for example, is a set of elements with a single operation. Usually we call it addition or multiplication, but it has to satisfy certain properties.
Like associativity and the existence of an identity element. I vaguely remember those terms from way back when.
Yes, exactly. Rings are a bit more complex. They have two operations, usually addition and multiplication, and they satisfy a few additional properties.
And fields are even more specialized, right?
Right. A field is a ring where every non-zero element has a multiplicative inverse. So like the rational numbers, the real numbers, those are examples of fields.
So abstract algebra is like, it's like we're building this framework for understanding different kinds of mathematical systems. It's like creating a blueprint for how mathematical objects behave.
That's a great way to put it. It allows mathematicians to study the underlying structures of different mathematical objects and discover relationships between areas of math that might seem totally different.
Like having a master key that unlocks all these different doors to various mathematical realms.
The beauty of abstract algebra is its power to unify and connect different branches of math. It's about finding the common threads running through these seemingly disparate areas of study.
It's fascinating how mathematicians can find those underlying patterns, those structures that link these seemingly different concepts together, like they're revealing some hidden architecture of the mathematical universe.
And those connections, they often lead to new insights, new discoveries that push the boundaries of mathematical knowledge even further. It's an ongoing process.
So we've talked about how math helps us understand the physical universe. But the book also explores how it's used to, describe and analyze complex systems in other fields.
Right. Mathematical modeling has become indispensable in areas like economics, biology, social sciences, even the arts sometimes.
It's incredible how math can be applied to such a diverse range of subjects.
Mathematical models allow us to represent these complex systems in a simplified way, making it easier to analyze their behavior, make predictions about their future states.
It's like how economists use models to try to predict market trends, or how biologists use them to simulate the spread of diseases.
Exactly. Mathematical modeling provides us with a really powerful set of tools for understanding and managing complex systems. It helps us to see the underlying dynamics that shape our world.
It's remarkable how math has become so integral to so many different disciplines. It really is a universal language with incredible reach.
It is. It's a language that can illuminate and solve problems in just about every area of human endeavor. And I think the more we learn about math, the more we realize how much more there is to discover.
This deep dive has already been such an incredible journey, and we've only just scratched the surface. But I feel like I'm already starting to see the world in a whole new way.
That's the power of mathematical thinking. It opens up new perspectives, new ways of understanding.
But our exploration doesn't end here. There's still one more part to go.
In part 3, we're going to continue our journey, uncovering even more of math's secrets and its beauty. We'll delve into the foundations of mathematics, explore the concept of mathematical proof, and maybe even touch on some of those philosophical implications of this extraordinary field of knowledge.
And we're back for the final part of our deep dive into all things math.
It's been quite a journey, hasn't it? From, just what a number is all the way to abstract algebra and non-Euclidean geometry. Wow.
It really has. We've seen how math can help us understand the universe, from those tiny little particles to the structure of space and time itself. It's pretty amazing.
And we've also talked about how math can be used as this problem-solving tool, not just in physics, but in engineering, economics, biology, so many fields.
Right, but now it feels like we're going even deeper
Uh-huh.
to the foundations of it all.
I think that's a great way to put it. We're going to examine the bedrock upon which this whole structure of math is built.
Yeah.
And the book spends some time talking about set theory.
Ah, set theory. It's always seems so fundamental, but also a bit mind-boggling, to be honest.
It is. It's basically a way of formalizing the idea of collections of objects. We call those sets. Sounds simple, but it leads to some really profound discoveries and even paradoxes.
Oh, yeah. Like, I remember Russell's paradox. That one always kind of messed with my head. It showed how even something as basic as sets could lead to contradictions.
Exactly. Russell's paradox, it demonstrated that if you just approach set theory naively, thinking any collection can be a set, you run into trouble. Like the classic example is the set of all sets that don't contain themselves.
Yeah, it's like a self-contradictory loop. How can a set both contain and not contain itself? It's just weird.
It is weird, and it's a paradox. It forced mathematicians to re-examine those foundations of set theory and come up with more rigorous axioms. They had to refine the system to avoid those contradictions.
So it was like a crisis, but one that ultimately led to a deeper, more solid understanding of the basis of math.
That's a good way to think about it. And set theory, even though it had those initial paradoxes, it became a powerful tool. Like, it helps us understand the structure of math itself and even led to new branches of math like topology.
Topology, yeah, that's another one of those mind-bending concepts the book mentions. I've heard it described as like rubber sheet geometry, which is a pretty cool image.
That is a good way to visualize it. It's about studying those properties of shapes that stay the same even when you stretch, twist, or bend them. No tearing or gluing allowed, though.
So it's about those fundamental properties that don't change, regardless of the specific uh, size or proportions of the shape, like the unchanging core of something.
You got it. Topologists, they're interested in things like connectedness, holes, boundaries. Those properties stay the same even if the shape itself is changing.
And the book talks about how topology has applications in other fields too, like physics, computer science, even data analysis. It's pretty amazing.
It's true. Topology is becoming increasingly important for understanding those complex systems,
Mhm.
especially the ones with, all those intricate connections and patterns. It's like a whole new way of looking at complexity.
Okay, so let's talk about another fundamental concept, mathematical proof.
Mathematical proof, it's really at the heart of mathematics. It's what sets it apart from other fields.
It's about establishing the truth of a mathematical statement with absolute certainty, right? There's no maybe or probably in a proof.
Exactly. A proof is a rigorous logical argument. It has to demonstrate the validity of the theorem, and it's built on those established axioms and rules of inference. There's a real beauty to it.
It's like building a solid structure, brick by logical brick, no gaps, no shaky foundations.
I love that analogy. And there are different types of proof, each with their own kind of logic and elegance. There's direct proof, proof by contradiction, proof by induction.
Proof by contradiction always felt a bit like a clever trick to me. You assume the opposite of what you're trying to prove and then show how that leads to a contradiction. And bam, you've proven your original point.
It is a clever strategy, and it's surprisingly powerful. A lot of famous theorems were proven using proof by contradiction.
And then there's proof by induction. It's kind of like a domino effect. You prove it's true for the first case, then you show that if it's true for any case, it's true for the next one. And that logic just cascades down the line.
Exactly. You've got those two steps, and you've proven it's true for all cases. It's a beautiful example of how a simple logical principle can lead to these far-reaching truths.
It's kind of like math magic. But of course, it's all based on solid logic and reasoning.
That's what's so cool about mathematical proof. It's this blend of creativity and rigor. That rigor is what gives math its power, that lasting certainty.
It's what allows mathematicians to build on what came before and create this vast, interconnected system of mathematical truth. And
Hmm.
and that system, it spans centuries and continents. It's pretty incredible.
It is, and that system of truth leads to all sorts of philosophical questions.
Well, the book definitely gets into some of those philosophical implications, doesn't it? Like those big questions about the nature of math itself. Is it invented or discovered? What's the relationship between math and reality? It's pretty deep stuff.
It is deep. And one question that has always fascinated, both philosophers and mathematicians is math something we create, or are we uncovering something that already exists?
Right. And there's no easy answer to that. Sometimes I think math is this pure, abstract system that we've built, but then other times it feels like we're stumbling onto these deep truths about the universe that were, always there, just waiting to be found.
I think that's the beauty of it. The book doesn't give us any definitive answers, but it does give us these thought-provoking insights, encourages us to wrestle with those big questions.
It challenges us to think critically about what math is,
Yeah.
what its role is in our understanding of the universe, and even what our place is in that universe.
And for me, that's what makes this whole deep dive so rewarding. We haven't just talked about the what of mathematics, but the why and the how. We've gotten a glimpse into the heart of the discipline.
We've seen how math is dynamic, how it's always evolving, pushing those boundaries of what we know.
Hmm.
And I think we've also gained a deeper appreciation for its beauty, its power, and just how profound the implications of math really are.
We've come to the end of our deep dive, but of course, the exploration of math doesn't stop here. It can be a lifelong journey.
And we encourage you, dear listener, to keep diving deeper into those topics that sparked your curiosity. Don't lose that sense of wonder.
There's a whole universe of mathematical wonder out there waiting to be discovered. And as we've seen, even those who consider themselves, experts in math can always find something new to learn and explore.
It's a good reminder that even in a field as rigorous as math, there's always room for curiosity, creativity, and that sense of awe and discovery.
So keep exploring, keep asking questions, and keep pushing the boundaries of your own understanding of math. Until next time.